Alec, are you ready?
Yeah, I'm ready.
Okay, great. So our next speaker is Aleix Gimenez-Grau. He will tell us about bootstrapping holographic defect correlators in equal form. Please,
thanks for the introduction. I'm very happy to have the opportunity to present this paper that we did together with Julien Barrat from Humboldt University and Pedro Liendo from the SE. And it's all it's going to be work in n equals for super young meals. So in particular, the characters of the story I'm going to tell today are the stress tensor multiplet, which some people also call the 20 prime multiplet, which is just a product of two of the fundamental fields in n equals 4, and you just take a symmetric Dirichlet combination. Okay, and correlators of this operator have been studied at weak and strong coupling, and it's very well understood in the literature how to do that. Now, the other operator I'm going to consider is the supersymmetric Wilson loop, where we couple the loop also to some scalars such that we preserve some supersymmetry. And again, this observable is also understood how to calculate it in the planar limit by resumming the Feynman diagrams or by using supersymmetric localization. But today what we do is to actually consider the interplay between the two observables. So we want to consider the first non-trivial correlator that involves both Wilson loops and local operators. So the simplest such observable is a 2-point function of local operators in the presence of the Wilson loop. So this double bracket notation means that we are normalizing all of our correlators by the expectation value of the loop. So graphically, this is the kind of observable we are interested in. And we are going to be working in planar n equals 4 super young meals. So we send the number of colors to infinity, keeping the top coupling fixed. And at the very end, we send the top coupling also to infinity. So in this particular regime, this observable we are interested in starts with some order 1 contribution. You get some lambda over n squared corrections. And here you would get some infinite tower of 1 over square root of lambda corrections. Okay, and a very easy way to understand the power counting of these terms is to look at the ADS5 description. So basically the order 1 term is just some disconnected diagram in ADS. Then this leading order correction corresponds to some factorized diagram. And what we are interested in is the first non-trivial correction. So this 002 is described by some diagram where there's some interactions in the bulk. So that's really what we want to compute today. But we are not really going to compute the Witten diagrams. So what we are going to do is we are going to use Bootstrap to fix the full correlator, and we are going to use some technique called the inversion formula. Okay, so what we need is actually to have some crossing equation in analogy to usual CFTs without defects. So let's review the kinematics. So this 2-point function we are interested in, it depends on two space-time cross ratios, which are analogs of the cross ratios in the usual CFTs without defects. And then here we have some R-symmetry cross ratio that counts the 3 R-symmetry channels that are present in this setup. And now, given this correlator, there's 2 different ways to expand it. So you can either expand it in the bulk, so you can fuse 2 bulk operators and you can replace them by an infinite sum over local operators. But in defect CFT, the new possibility is to take some bulk operator and replace it as a sum over operators that are localized on top of the defect. So that's a new OPE that you are allowed to do in defect CFT. So in particular, our correlator, by doing these 2 types of OPEs, contains an infinite amount of CFT data. So you can either extract CFT data in the bulk. So here you have an infinite sum over bulk operators. You have some OPE coefficients that contain dynamical information, and you have some conformal blocks that capture the kinematics. And similarly, you have an infinite sum over defect operators with some OPE coefficients. Now, what we are going to do today is to reverse the logic and to actually impose that the correlator is consistent with these 2 expansions and use this consistency condition to fix the full result. And in order to do this, in order to impose this consistency, what we are going to use is the inversion formula. So this is a formula derived by Simon Caron-Quote, which tells you that from the discontinuity of the correlator, by computing some integral against some kernel and computing some infinite sums, you can reconstruct the full correlator again. So the discontinuity is just defined as usual in complex analysis. And the main point of this formula is that you only need the discontinuity to reconstruct the full correlator. So even though you don't really need the full, you don't know what the full correlator is, it turns out that the discontinuity is much simpler than the full correlator. So if you manage to compute the discontinuity, you can actually reconstruct the full result. And that's why we can do Bootstrap in this setup. So what we want to do is that we want to compute the discontinuity. And remember that we are considering a 2-point function of the 20 prime operator. So we are going to use the bulk OPE. So we multiply two 20 prime operators, and the first thing that appears is the bulk identity. The next thing that appears is the 20 prime itself. And finally, here you get some infinite sum, which in principle could be very complicated. Now, the thing that is going to allow us to succeed is that we are using some simplifying assumptions. So first of all, we are working in the planar limit. And in the planar limit, only single and double trace operators can appear in this OPE. Because otherwise, like multi-trace operators, they would be suppressed in this large limit. The other simplifying assumption that we are using is that we are working in the strong coupling regime. And in this regime, unprotected single trace operators, so for instance, the Konishi, they would acquire very large anomalous dimensions, so they decouple from the spectrum. So basically from this discussion, what we conclude is that this infinite sum here, it runs only over double trace operators. So it's just products of 20 primes where you have a bunch of derivatives in between. And these operators are very well understood. So we know the form of the anomalous dimensions. So here the observation is that when you compute the discontinuity of these blocks, the discontinuity is proportional to the anomalous dimension. But this anomalous dimension, it's actually subleading at the ordering perturbation theory that we work. So basically discontinuity is 0. So the discontinuity is so the bottom line of this whole discussion is that by taking discontinuity in this equation, we reduce this complicated infinite sum into a sum over two terms that we understand. And as I was saying before, once you know the discontinuity of the correlator, you can reconstruct the full object. And that's what we did. So as I was saying in the introduction, we are interested in this leading non-trivial correction, which has 3 different R-symmetry channels. And then the leading asymmetry channel is the simplest one. And you can see that all these correlators are actually really simple. So they only depend on logarithms. So there's no polylogs involved or any complicated functions. And then everything else are just like rational functions of the cross ratios. So we're really surprised to find such a simple correlator in this context. So that's what we wanted to compute. So maybe let me conclude with some outlook. So as I was saying, we computed the 2-point function of the 20 prime operator, but we actually also considered chiral primary operators that are length 2, 3, and 4. And in principle, our methods could also work for bigger operators. It's just a matter of computing everything in Mathematica. Now, the motivation to study more larger operators is that perhaps it's possible to find some closed formula. So perhaps in some nice representation like Mellin space, it would be possible to derive the full correlator for arbitrary length. Another idea is that our correlator, it captures an infinite amount of unprotected CFT data. So maybe it would be interesting to see if some of these, for instance, 1-point functions in the bulk, if they could be also obtained from integrability. They are known at strong coupling from our result, and they are also known at weak coupling from some perturbative calculations. So it would be nice to see if there's some description from integrability. Another idea is that here we did Bootstrap, but there's actually a nice description in terms of Witten diagrams in ADS. So in principle, these Witten diagrams, they could be very complicated, but we saw that the result is actually very simple. So one of the ideas that we have in mind is to try to do the exact calculation in ADS and confirm that we obtained the Bootstrap result. Some other ideas is to look at different setups. So for instance, the main assumptions we had to use were planarity and strong coupling. So these are CFTs that are described by holography, but we know many more examples. So we know that besides n=4, there's also ABJM, or there's the 62,0 theory. And all these models, they also contain interesting defects that could in principle be studied with the same methods. And finally, let me mention that we actually didn't really need to use supersymmetry for our calculations, So in principle, everything we did also applies to condensed matter systems. And that's what we did in this paper with Pedro this summer, where we studied some monodromy defects. And there's now work in progress to extend this work to some quantum impurities. So that's everything I wanted to say. So thank you very much. I'm looking forward to the questions.
Okay, thank you, Alec, for the very interesting talk. And now we have time for questions. So you already wrote about this million space. So do you already see some benefits in rewriting the million space, particularly written diagrams, calculations looks nice.
Yeah, so roughly speaking, the idea is that instead of having functions of the cross ratios, you should get some meromorphic function of ST and U or something like this. So then it might be easier to guess the structure of the correlator. So that's and especially the motivation to look at Mellin space is that when there are no defects, it was actually possible to guess the 4-point function of chiral primary operators in Mellin space. But in position space, the formulas were too complicated. So that's why we believe that maybe in Mellin space, we are going to be more lucky. But even in position space, we could guess some parts of the correlator.
So could I ask, in the position space, can you write it neatly in terms of the single value harmonic Fourier logarithms, or it's still messy?
But it's like the result, it only depends on logs. So you don't even need any.
Yeah, but I mean, so some of these combinations, maybe they look a bit nicer and more suggestive.
Yeah, that might be, we didn't really explore it, but this might be true. But yeah, like actually we were expecting like higher kind of polylogs. We didn't really expect only logarithms in the correlator. That was a surprise.
Because in principle, all your assumptions, they would work for the next orders in the lambda. Right? The only problem is having dimensions. I don't know how, to which order are they know.
Yeah, exactly. So also there's also some technicalities on how you compute this result that we are not sure if they hold at higher orders in perturbation theory. So in particular, this inversion formula that reconstructs a correlator from the discontinuity, sometimes it misses some contributions. And we are not entirely sure if this could happen at higher orders in perturbation theory. So that's something we would need to explore.
There is a question from Carla. I don't know, Carla, can you ask?
Yeah, I cannot read the chat, unfortunately.
What is OLL capital? What is this?
Yeah,
this
is a length L single trace operator. Like
what is this operator? Yeah.
OL, it's like what many integrability people would call this trace of Z to the L.
Ah, and Z is what is that?
Just
Phi 1,
basic
let's say, plus I, phi C, phi 2, something like that. That's it.
Thank you.
So it's just like the kind of the single letter half-BPS operator.
Thank you.
Sorry, let's see. My question was about the log 1 plus square root ZZ bar term in the answer, and why there is a way to understand why that appears.
Exactly. So there's some background noise. Can someone mute himself? Yeah, thanks. Yeah, that's an excellent question. So these logs here, of course, they correspond to defect anomalous dimensions. And these ones here, they are a bit surprising. So because in the bulk, there are no anomalous dimensions. So I don't know, it's, yeah, like we didn't really expect them, but all I can say is that they don't really give contributions to bulk anomalous dimensions. So even though this might look singular in the bulk limit where Z equals to 1, actually no anomalous dimensions are generated. So, but I don't have much more to say, unfortunately. Does this answer the question?
Yes, thank you.
Okay, So is there other questions? Well, in any case, we will have time for joint discussion after the last talk. So, and let's thanks Aleix again and stop recording.